Okay, I think we should start now. So let me remind you what we've learned last time, okay, or last week. Last week, we introduced, instead of Fourier series, we have another kind of, transformation of a function, okay, which is the Fourier transform. Which looks like the Fourier coefficient we try to compute, but now it's not defined on the integers. It's defined on an integral over everything. Okay, so it's fx e to the minus 2 pi I xc dx. Okay, this is the Fourier transform of a function. And then we define, in order to do this kind of integration over everywhere, we also need to define some good function space so that this kind of transformation or this kind of transform, it does make sense, right? So we define what is a Schwarz space. Which is all these kind of functions that are very, very smooth and it decay very, very, very fast, right? So all this kind of thing, x to the power k, and you can take partial to the power d over dx to the power L of this function. It's always less or equal than some constant. Okay, for any k and l. Those kind of functions, which you can take an arbitrary derivative to it, and meanwhile you can this arbitrary derivative can decay as faster than any polynomial. Those kind of function we call it a Schwarz function, and those kind of function form a space, so-called the Schwarz space. Okay, and the last time we mentioned that. Although it seems that nobody are really in this space, other than those kind of variation of Gaussian, right? E to the minus x squared. This kind of function are in this space. But other than this function, it seems that nobody are really in this space. But we mentioned that no, not really. Those kind of function which are really smooth, but with compact support. Those smooth function with compact support are also on this space, okay? And those functions, you can find a lot of things, and these functions can help you in the future when you do analysis, okay? You can try to do some kind of cutoff, which you will see in the future, okay? And then, as an example, we show that if you have this kind of Gaussian, this function, and if you try to take the Fourier transform of it, what you can get is, itself. Okay, you can get this Gaussian itself. So, which means, at least for this only example, we are able to find the Fourier transform of it. Okay. And now, this is only a start. Well, as we mentioned before, we may have a lot of functions in this Schwarz space. And now we only know this one function, what its Fourier transform looks like. Then how can you deal with other functions? This might be a very hard problem. But what we can say is, at least on this function space, you will have a lot of very good properties of your functions, okay? So before that, let me try to say a little bit more about this, these examples, which can be seen as a corollary to these examples, which is when you try to do a dilation of the Gaussian, then what you can see is, well, the Fourier transform looks still somehow similar to Gaussian, okay? Which is, if you have so-called k delta, looks like delta to the power 1/2 minus 1/2 times e to the power minus pi x squared divided by delta. If you have this kind of function, then if you take the Fourier transform of this function, what you will get is e to the minus pi delta psi squared. Okay, so if you want to do a dilation on the, well, so-called the frequency space, then on your phase space or configuration space, what you can get is this kind of dilation and multiply by this constant. Okay. The reason why we're interested in this kind of well, special case or this correlate to this well, theorems or this example is simply because by this kind of thing, when you see Gaussian, okay, what kind of function you are looking for? You try to look at this kind of function, right? Decay very fast and somehow concentrate on this well, somewhere close to zero domain, right? And I think you also learn this kind of normal distribution. Normal distribution simply say that, okay, around this zero, around x equals to 0, the probability is very high, but if x is super big, then the probability is very low, and so on. The distribution of probability is very low. Okay, and now what happens is, if you try to do a dilation, which can somehow squeeze your Gaussian a little bit, which makes your Gaussian slightly more concentrated, okay? Then if you try to make your Gaussian from this kind of thing to this kind of thing, then let's see what happens, okay? Then that means you try to squeeze this part. You try to squeeze this part and make it a little bit more narrow, okay? So that means what you're trying to do is you try to change your x to, for instance, here your x is from -1 to 1, and well, it's very wide, and then you want to make this very wide domain to be something slightly not so wide, for instance, -1/2 to 1/2. The concentration becomes something like this. Then what you try to do is you want this 1 and -1 to be 1/2 and -1/2, right? So what you want is, well, x squared divided by some small number, so that when x equals to, for instance, square root of delta, well, this evaluation, well, the value of this this part, it's the same as the value as, well, you plug in x equals to 1 here, okay? So this is the meaning of this delta on this function, which is if you take delta to be smaller and smaller, you try to squeeze your Gaussian a lot, okay? So you try to make your Gaussian to concentrate on this, well, this y-axis more and more, if you take delta to be smaller and smaller. But meanwhile, you can see that, well, if you try to do this kind of squeezing operation, what you also want is, since Gaussian, it's somehow like a distribution, right? It's a distribution, so what you want is the total integration of Gaussian still keeps to be 1, okay? So if you want to say that, okay, e to the minus pi x squared divided by delta dx is somehow equals to e to the power minus pi x squared dx, then what you want is, well, if you want to keep these two things the same, what you want is you have to divide by delta to the power 1/2, so that this can be eaten by dx, and you can do a change of variable, then these two guys are equals to each other. So which means this kind of dilation of this Gaussian is not only squeezing it, you have to keep the area under it the same, you will have to make this point a little bit higher, okay? So which means if you want to change, from this Gaussian, for instance, this is Gaussian, e to the minus pi x squared, to somehow squeezing it, then what you really want is, well, it's decaying. What you really want is you want something very high, okay, but very narrow. So this can be seen as y equals to e to the power minus x squared divided by tau times 1 over tau to, well, delta to the power half. Okay? So this kind of operation is somehow kind of concentrate on this x equals to 0 or y-axis. Okay? And I hope this can somehow remind you something that we mentioned before, which is something we've learned when we try to learn the Fourier series, that is so-called the good kernel. Okay, you can see that this kind of function is also somehow, well, when delta tends to 0, it also somehow concentrate on this 0. Okay, concentrate on x equals to 0. So which means it's kind of an analog of the good kernel that we've learned before. Actually, this kind of Gaussian is the original setting of the good kernel. So people always see this kind of Gaussian to be the first kind of a good kernel. Okay? And moreover, if you try to see what we had before, that is, okay, your Gaussian somehow likes a good kernel. Try to squeeze it, and then it will behave like something concentrate on this 0. Okay, if you try to look at this k delta, which is delta to the power minus half e to the power minus pi x squared over delta, then the Fourier transform of it looks like e to the minus pi delta psi squared. Okay, so for this function, you can still try to play with it and see what happens to this function. For this function, what happens is, well, you somehow not squeeze it, but try to expand this, well, standard Gaussian. Okay, because you can see that when delta equals to 1 over square root of delta, when psi equals to 1 over square root of delta, this equals to e to the power minus pi, right? So which means at this point, at delta equals to 1 over square root of delta, well, it should take the same value as the value evaluated 1 of this function, right? So which means it will somehow be a very fast function, okay? You try to expand your delta, well, your Gaussian function, okay? So in this spirit, you can somehow see that, okay, you try to make your Gaussian this major part of your Gaussian, or somehow you can think it's more or less like the support of your Gaussian to be smaller and smaller and smaller, but the Fourier transform of such function will have, well, somehow bigger and bigger and bigger support, okay? And this is actually a very good example or understanding of the meaning of uncertain principle, which is, well, for the phase space and frequency space, their support may somehow be complement in some sense. Or at least you have to say that there is no function who is both compactly support and the Fourier transform of this function is also compactly support. Okay, this is actually an exercise on your on your textbook, but I'm not going to assign it as a homework because well, it's a little bit too hard for you and it's not necessary. But this is a very interesting property about Fourier transform, which is if you have a function that is compactly supported, then the Fourier transform of it will not be compactly supported. Okay, and if you are interested, you can read the last section of this chapter, which is an uncertain principle. Good. What happened? Anybody else see this kind of well, problems about the video? Is that common for you? Why is that? Let me try to use some weird network. Maybe this will work better. There is somewhere. Well, let me try to change this network and see if it works better or not. It's supposed to be a little faster if I change from wireless to weird, but anybody else see this kind of problems?
Actually, like I asked like privately a few minutes ago, and she has this problem. She also has this problem.
Oh, that's weird. How about now? Does it look better?
I think
not really.
Not really, actually.
Well, I don't know why. It should be fine on my side. Well, why it should well? But I mean, I didn't change my network environment. How about you, Rongchen? Did you see anything, or did you feel it's not smooth?
Yeah, it gets stuck like free for 1 or 2 seconds, and then just another frame.
Yeah, but how about my sound? Well, maybe you can. Well, for this video, it might be slightly.
Yeah, I think like for the sound, it's like smoother, but like the video really got stuck frequently.
Okay, but for video, I think it should be okay. I guess. If sound is fine, then I think should be okay. For the video, well, I may try to write it slower so that you will not feel it's not so smooth. Okay, because after all, you will hear what I'm saying, and this kind of video is well, you can think it's just some kind of stuck again. Let me see. Why is that? Is there any? I didn't change anything, so it looks worse than before, right? It was worse than before, than for instance last week. Is that true?
Yes, it's worse than last week.
That's weird. Why is that? I didn't do anything. So I close my video for my face, my camera. So does it looks well? Yeah,
Not really,
I also see
actually.
that. I also see that. Well, why is that? Okay. Anyway, I think well maybe I'll try to check that well after class. As long as you can hear me clearly, I think I will try to write everything very slow here. Okay.
Yeah. Okay.
Hopefully it will getting better. But I don't see any problems of the network at this moment. Why is that? Anyway. Yeah, so hopefully it's not a big deal. I will try to write it slowly, okay?
Professor, you connect to your VPN.
I didn't, well, did I? Let me see. Maybe that's a problem. Did I open my VPN? I don't think I opened it. No, I didn't. I didn't. It's not on my VPN.
Mm-hmm.
So yeah, so I think it shouldn't be like this. Did I use VPN here? No, I don't think I use VPN. Well, I think the only thing changes yesterday. I just update my Windows, and I just will get some patches. And will that be a problem? Anyway, yeah, if that would be a problem, then maybe I will try to fix it next time. I may try to use another computer. Maybe that should be fine. But in our, yeah, but I will write it slowly. Okay, maybe that works. Yeah, why is that? I'll write it slowly so that you can try to watch it as a PPT. Okay, maybe that will work. Anyway, I heard that, yeah, maybe this this Windows patch, this update has some problems. I think I saw some news about it. I didn't know, well, it will be as bad as this kind of thing. Anyway, yeah, I think I will fix it. Well, but right now, let's just try to watch some PPT, okay? Maybe, yeah, maybe it's not so bad, I hope. So this just tell us this kind of idea, which is more or less like an uncertain principle, which says that you cannot have a function and a Fourier transform of a function to both to be compactly supported. This is a very interesting idea, and in the future, if you try to do some kind of research, this might be important for you if you try to do some research on Fourier analysis. Okay, and okay, so talking about the good kernel. Okay, the good kernel is something like we try to make this kind of function to concentrate on one point, which is the origin, or x equals to 0. So talking about this, we probably need to first say something about the good kernel's properties, just as before. But of course, now the parameter here is delta instead of n, capital N. And then another thing is, then under our new conference or this configuration, probably we need to define the convolution in a new content, right? Based on the new Fourier transform content. And then maybe we can still say that, okay, a good kernel is still a good kernel, so that if you try to convolute with a function with good kernel, as you take the parameter tends to 0, then you get this function back. Okay, so first, let me say this k delta is again a good kernel. Okay, which means it satisfies the following 3 properties. If you take the total integral among the real axis, you'll get 1 for k delta, for any delta. Okay, and 2, if you take from, well, if you take this absolute value of this k delta, is less or equal than f, well, for sure. And the third, if you have any data which is greater than 0, and you do a cutoff as the origin, okay? If you do this kind of cutoff, and then you take this integral, then you can see that eventually everything will try to squeeze, and you will have nothing left well, outside this this cutoff. Then it will tends to 0 as eta tends to 0. Okay. So this is why we call this K delta another good kernel. Okay, and well, let's call it a theorem. This K delta is a family of so-called the good kernel. Okay. The proof for all these properties are kind of easy. The first two, well, you just do the integration. Well, you just do the change of variables, and K delta is actually a positive function. And for
Professor,
three,
isn't it shouldn't it be like as eta tends to infinity?
I'm sorry. Delta. This delta is the parameter of this, well, K, right, of this kernel. Oh, thank you for correcting me. It should be delta. It's just like this capital N. Okay, as we mentioned, you take delta to be smaller and smaller, you try to squeeze these functions more and more and ask it to be more and more concentrated on the origin. So for any fixed interval outside of it, if you keep squeezing, then everything else outside will tend to 0. Okay. And the proof is well, it's pretty straightforward. Well, the only thing that we might need to prove is the third one, right? For the third one, well, you can see that x is greater than eta, K delta x dx is equals to, you do a change of variable, this K delta equals to this, then if you call this new variable to be y, then y is actually, well, is actually equals to x over square root of delta, right? So it's y greater than eta over square root of delta e to the minus pi y squared dy. Okay, so maybe I should write it carefully. Delta to the power minus a half e to the power minus pi x squared over delta dx. Okay, and you call this y to be x over square root of delta. You got it's equals to this. And you can see that if delta tends to 0, well, if delta tends to 0, this kind of, well, square root of delta will tends to 0. So it will be y greater than some big number, and this big number tends to infinity. And we know that this integration converge, right? So you can take from minus infinity to infinity, and e to the minus pi y squared dy, it equals to 1, right? So which means if you try to look at the tail of this integral, it should tend to 0. Okay? That clear? This is the definition of convergence, right? If you want, you can see that is y is greater than r, and r tends to infinity. Okay. So this K delta is a so-called a good kernel. And then to use this kind of good kernel, we will need this kind of so-called the convolution, right? The convolution of this functions on the Schwarz space. Now it's not a periodic function. Okay, so fg in the Schwarz space, what we have, well, their convolution is something you can imagine. F convolve with g. Now it's not on one period, it's on everywhere. Okay, f x minus y or x minus t, gt, dt. Okay, same as before, but I just change y to be t so that to make it different from what we had before. Okay, and then we define this kind of convolution, the natural corollary should be, if you define this convolution, then the convolution to a good kernel should be approximation of your function. Now you have a Schwartz function. Then what we have is you convolute with this kind of kernel. It tends to fx uniformly in x as delta tends to 0. Okay? Now you have everything exactly the same as what we had before, right? The only difference now is, well, now your x is on the whole real line. So you could have x to be anything. It's not necessary to be restricted on a bounded domain, like from minus pi to pi. It could be anything, any real number. And the proof is exactly as before, okay? But I still want to write it so that you can see, well, when we try to deal with those kind of whole real line problems or the infinite domain problems, how we can deal with those, how we can use a decay condition of a function. Okay. First, you want to show this fx minus fx convolute with this good kernel, which is this one, say x minus t times k delta t, and subtract this fx. Of course, if you, since the integral of k delta t is 1. So basically, you want to show that this can be arbitrarily small as delta tends to 0. Okay? So it's equals to, from minus infinity to infinity, k delta t times fx minus t minus fx dx. You want it to be, you want it tends to 0 as delta tends to 0. Okay? So then let's see why it could tends to 0. Okay, so if we try to use our old idea, okay, then probably we want to split it into 2 parts. One part is, well, since we want to use the condition of the good kernel, so maybe we would like to say some small eta, right? Then we try to split this whole real line to be, okay, t, I'm sorry, this is dt, this is dt. If t is not so big, if t is very small, then we know that, okay, this part, this function, when t is very small, is bounded above, right? Whatever it is just some bounded function. So in that case, you only take the integral of k delta when, well, I'm sorry, when t is big, okay? So it can be split into 2 parts. One part is, okay, if t is bigger than some eta, you have k delta t fx minus t minus fx dt. And for this function, and plus t is less than eta, k delta t fx minus t minus fx dt. Okay? And for this function, you can see that this function, no matter what you have only fx, f function. F is a Schwartz function, so this part is bounded above. This part is bounded above, bounded function. So this part, we can use proposition 3 of the good kernel. It will tend to 0. It will be super small, okay, as delta tends to 0. Now, the only problem now is, what if your t is not so big, it's super small? If t is super small, then we cannot do any estimate relies on this k delta t, right? Well, it may not help us, it's just something that will not hurt us. then if t is not very big, what we really want now is, okay, if t is not very big, then fx minus t and fx should be very close if t is very small, okay? But if we really want to say this kind of thing, what we really want to say is, okay, for arbitrary x, this fx minus t minus fx should be very, very small, because you want to say this convergent is uniform in x. So which means you want to say any x, you can find 1t or 1 eta, so that if t is less than eta, fx minus t is always very close to fx, right? So what you really want now is you want f is uniformly continuous in not a bounded domain, but in R. Okay? So that we can choose some eta, so that if t is less than eta, then for any x, you will have fx minus t minus fx is very small. Okay? So as long as we can show that f is uniformly continuous, we are done, right? We can use epsilon delta language to choose some eta to be small enough, and then to choose delta to be small enough, so that, well, both of these two terms are very small, okay? So now the only problem for us is, well, why f is uniformly continuous in the whole real line? Why is that?
Because f is in the Schwarz space.
It's in the Schwarz space, then how does it help us?
There should be a maximum value of f.
And
we can like claim like f satisfies like a Lipschitz condition, and then it is converged. It continues uniformly because it has a maximum value in its domain. And,
well, if you only have this kind of bounded condition, right? It has a maximum value on its domain, then that means you only have a bounded condition. But bounded condition may not be as strong as uniformly continuous, right? But you're very close. You're very close. Well, if you want to show something is uniformly continuous, the function itself is bounded. This may not be enough. However, if you know the derivative of this function, it's bounded. Okay? It's bounded in R. Then this is enough. Why is that?
Because of mean value theorem can represent it's an equivalency of Lipschitz condition.
That's right. So you can see that f prime is bounded above in R. Okay? So if you have fx minus fy, by the mean value theorems, this is mean value theorems, you can get it's always less or equal than the maximum of f prime of x, right? Well, f prime of t in R, times x minus y. Do you still remember this? This, this kind of mean value theorems? Fx minus fy is equals to, there must exist some kind of theta between x and y times x minus y, right? So if you take this part to be maximum value of all the f prime, then of course this part, the right hand side is greater than the left hand side. That clear? So that means, okay, no matter, well, your x and y, well, which x, which y you have, as long as your x minus y to be small, your fx minus fy is also very small. Okay? This is one idea about how you can show a function is uniformly continuous. This is so-called the function is Lipschitz continuous. It's actually a stronger condition. But of course, in our textbook, he also introduced another kind of, a way to prove f is uniformly continuous. This kind of way is you don't really use any derivative of this function. And you can show that as long as your function has some decay, as long as your function is decaying, at infinity, or as long as your function is decaying to 0, then your function could be uniform continuous. Okay, so it's not necessary to be Lipschitz continuous. It's not necessary to be the derivative is bounded. Okay, you can show that by another way, but I think this way is easier for you. Okay, so we've shown that f is uniformly continuous. Then of course this part can be bounded about by something like t or by eta, right? So which means you can take arbitrarily small eta, and based on this eta, you can take delta to be small enough, and so that both of these two terms, you take the addition, is smaller than epsilon. Okay? So I will not finish the proof here, and you can try to finish it by yourself. Okay? Any question? Any question? Okay, so since we talked about this convolution, there are some propositions of the convolution just as before, okay? Just as the, convolution on the periodic functions, which is when f, g are in Schwarz space, then what we have is, you take the function's convolution, you still get a Schwarz space function. You still get a very good function. And you will also get f convolved with g is equals to g convolved with f. Moreover, which is also the reason why we're interested in the convolution operation, as before, the convolution of these two functions, you take the Fourier transform, is equals to the multiplication of the Fourier transform of these two functions. Okay? So, let me prove that. So you can see that this convolution is almost the same as an analog of the corresponding convolution operation of the periodic function. Okay, so let's prove it. Before we prove it, any question? Okay, so that's first trying to show that, you have two functions that are Schwarz function, then the convolution is still Schwarz function. Okay, this is a very good property. We know that we mentioned that the convolution actually can make your function smoother. But here, it actually says that, it will not only make your function smoother, but it will somehow keep the decaying condition of your function. Okay? So let's first prove it. Well, the proof, it used some kind of very interesting trick, or very common trick that we are going to use again and again for those kind of, infinite integration with this kind of variables. Okay, x minus t. So first, I will claim that because if you try to look at f convolved with g, what it is, it's integral from minus infinity to infinity, or well, let's say it's f t g x minus t. Okay, dt. Whatever, you can do a change of variable, which you use 2, and well, this is kind of easy to show. And then if you want to show that it actually has some decaying condition, well, this is something a little bit surprise us, right? You want to show this function, this new function, it will also decay as well as x goes to infinity. Then what you're trying to do is you're trying to do a multiplication on x to the power l. Okay, if you're trying to do a multiplication of x to the power l, then probably you want to multiply it with this g, right? X to the power l, gx minus y. And for this function, what we have is, if you take the supremum, which is a maximum of this function, okay, it can be bounded above by some constant that may depend on l times 1 plus y, you don't want x, to the power l. Okay, so which means you may multiply it, and then it becomes, if after you multiply this x to the power l, it becomes something like y1 plus y to the power l. Then you can see that if we can prove this, then that means if you multiply x to the power l, both sides of your functions, then maybe I should say here to be t, okay, to make our notation uniform. Then what you have here is it can be bounded about by some polynomial in t, right? And then this polynomial can be eaten by ft because ft is a Strauss function. So the integral of the among this t will give you a finite number. So which means, so this implies x to the power l times f convolved with g is bounded about by al times something like bl. Okay, because ft times 1 plus t to the power l is integrable. Okay, so then we got the decaying condition about the convolution operation. So now how can we prove this? We claim this is true. So why it is true? Well, in order to show this, what we try to show is, what we try to discuss is, since you have g with x minus t, right? So g x minus t is basically can be bounded about by anything, right? Anything like 1 over x to the x minus t to the power anything, capital N, right? So what you're trying to estimate is x to the power l times 1 over x minus t to the power n. This kind of thing. So how can we estimate this kind of thing? Okay. You want to estimate this kind of thing by something like t to some power, right? Then what we can do is we can argue whether this x minus t can be bounded by x or it can be bounded by t, or which variable will dominate of this term, of this guy. Okay, x minus t, which variable will dominate? So let's say if t dominates, which means if t can control some kind of x. Okay, what does that mean? that means if you have x minus t, well, it will be at most 3t, right? The worst case scenario is your x is equals to minus 2t, right? And the worst case for the lower bound is at least t. Okay? So which means your x minus t can be controlled by t. This is so-called, we can say that x minus t can be controlled by t. Okay? So of course, then we can say that, well, this kind of thing can be bounded about by, well, x to the L, g to something like, well, x minus t can be bounded about by, and of course, you also have t, well, x to the power L is bounded about by 2 to the power L, which is a constant, depends on L, times t to the power L. Okay, this is actually 2 to the power L. So this kind of thing can be bounded about by, this part, it doesn't matter. And everything can be bounded about by t, right? Some constant t to the power L. Okay, this is when t dominate. Then multiply by x is the same as multiply by t. And this part, it doesn't matter, right? It doesn't matter at all. Yeah, maybe you can make this kind of power lower, but we don't really need that, right? It doesn't matter whether we make this L or L minus 2 or L divided by 2 or whatever else. What we need eventually is this power to the L. The worst case scenario is fine. Okay, this is when t dominate. What if when x dominate? If x is greater or equal than 2t, which means your x will dominate on this x minus t. Okay, in this case, what we will have is x minus t, well, it can be bounded about by x, right? I think it's 3 over 2x, and bounded below by 1/2 x, right? So which means, okay, 1 over it to some power is still something bounded above by x, below by x, right? So that means x to the power L times gx minus t. We can take n equals to, say, L is bounded about by x to the power L, divided by something depends on L, x to the power L. Right? And it's some constant that depends on L. So combine these two, the supremum of x in R of this x to the power L, gx minus t is less or equal than some constant times, well, either it is a constant or it is t to some power. Okay, so you get this result. So again, you can see that from this kind of estimate, we didn't try to find anything like an optimal. We didn't try to find what is the optimal constant in front. We didn't try to optimize this, well, this power, okay? And we can even get something better, but it doesn't matter for our problem as long as we can get this kind of polynomial. As long as we can get this kind of polynomial, it is enough. for us. Okay, this is this is what analysis will really deal with problems. So for analysis, 1 and 1 million, they are almost the same because 1 and 1 million are comparable in some sense. Okay, so this is how you can show, and then you can show that F convolved with G is in Schwarz space, and at least for the decaying, if you try to take derivative of F convolute with G, what you can see is, since this kind of convolution, you converge absolutely, and it converges very well. So what you can do is you can switch the derivative and the integration. You may always be careful about this kind of switching the order of limit, but for this kind of functions, you are able to do that. If you are not quite clear about this, when you can switch the derivative and the integral, you can check the appendix of our textbook. Okay, so it's actually equals to F convolute with D over dx G. Okay, so since G is a Schwarz function, so this kind of thing is still well-defined things. It's actually a continuous function, and it's actually a very good function. So which means you are able to take derivative, an arbitrary derivative of this F convolute with G. Okay. Any question?
Sorry, Professor. Can you please explain where do we get like 1 over x minus t to the power of capital A?
Oh, of course, because G is a Schwarz function, right? So Gx times, maybe let's use another variable. Gy times y to the power n, if you take the supremum, is less or equal than infinity. It's less than infinity, right? It's a bounded number, right? For any y. So that means for any power, you should get gx minus t is less or equals to a fixed some number that may depend on n divided by x minus t to the power n. Okay, so this is a meaning of decaying faster than the polynomial.
Okay, I see. Thank you. Also, like for the last line of this page, like y is like in the on the left side there is k to the power of k, but like on the right side there's.
I'm sorry. Thank you. Yeah. So you can take arbitrary derivative directly to this function, right? You can see that. Okay, f convolute with gx is equals to the integral from minus infinity to infinity ft gx minus t dt, right? If you take derivative in x, then you take derivative in x, then we can change it to the inner part. You take the derivative of the whole thing, but ft it doesn't depend on x, so ft d over dx gx minus t dt, right? So this is actually f convolute with the derivative of g. Okay.
Yeah, got it. Thank you.
Any other question? And we also want to show 3, right? For 3, it's a little bit messy, but here I will not write it in a direct way or a straightforward way. Let me play a little bit trick here, because in the future we are going to...
Sorry to interrupt. Can I ask a question?
Of course.
Okay. Before we claim that the convolution of blah blah is less or equal to AL BL, and I am wondering why we can get BL here.
Why we can get what? DL here.
Yeah, DL.
Yeah, DL is simply because you can see that the integral from minus infinity to infinity, ft gx minus t dt, you multiply x to the power L, right? And then these two combined by this property is less or equal than the integral from minus infinity to infinity, ft times 1 plus t to the power L, okay, dt, times A, right? And then you can see that ft is a Schwarz function, so multiplying this polynomial is still integrable. So the integration is another function, where the integration, the total integration is another number, and then we can call it some number depends on L, BL. Okay?
I think I'm not okay.
Well, why is that? Well, which part is, well? So,
I
so
still,
which part? Yeah.
I'm still a little confused why we can get BL2 bounded.
Well, you can see from minus infinity to infinity, ft times 1 plus t to the power L dt. We are looking at this integration, right?
Yes.
And now this function, since f is in Schwarz space, so ft times 1 plus t to the power L, you can multiply some other, say, t to some power, okay? And it's still less than, well, it's still bounded, right? And you can think it that way. If you try to call it f, then this f is actually in Schwarz space. So if you take the integral from minus infinity to infinity, it's still bounded about, right? It's still integrable.
I am okay with ft multiplied by t to the L. But why we add another t, another ft is also in. Oh,
Why
okay,
this
I
is
got
still
it.
okay. So yeah, if you multiply any polynomial or take any derivative of a Schwarz function, you still get a Schwarz function, right? Because you can multiply any polynomial and it's still decaying for this function. And if you take derivative and it's still some polynomial times this function or derivative of this function, and it's still decaying, always decaying, okay? So this is why this integration is actually a bounded term. It's something bounded. It's something, I shouldn't say bounded, it's just a fixed number. It's just a number. Okay? Any other question? Okay, then let's try to prove 3. Okay, for 3, let me use a little bit tricky way to prove it. Well, if you really want to see that, you can try to write it by your own way, but this is slightly tricky because in the future, we will use this kind of trick again. And this trick is very standard but interesting, okay? But it's starting from the Euro way. Let's call this multivariable function, capital Fxy, to be, say, Fy gx minus y times e to the power minus 2 pi I x c. Okay? Then the convolution, and you take the Fourier transform, is equals to this d, you first take dy and then take dx, right? Why is that? F convolute with g is an integral. It's in x variable. It's an integral from minus infinity to infinity, and you have Fy gx minus y dy. Okay, if you want to take the integral, if you want to take the Fourier transform, it must be the integral from minus infinity to infinity, this function, right? And the times e to the power minus 2 pi I x c dx minus infinity to infinity. Okay, so this is actually a double integral of fxy dy dx. Okay, and now since this capital Fxy decay fast enough, which means the integral is convergence and is smooth in both x and y. Okay, you can see that our functions are pretty nice and decay. So what we can do is we can change the order of the integration. Okay, for this part, if you're not quite familiar with, again, it's on our appendix of our textbook. Okay, you can check it on appendix, why you are able to switch this order of integration. So it's equals to fxy. You first take dx, then take dy. Let's see why this magically can solve our problem. Okay, then that means it's fy gx minus y e to the power minus 2 pi I x c dx, then dy. Okay, then you want to take an integral first in terms of x. So this is actually a constant. Fy is a constant. Okay. Then what we want to do now is we can do a change of variable in terms of x, right? Then what happens is if you, well, you can either do that or try to write here as x minus y plus y. Okay, try to write here as x minus y plus y. And then what you will have is an additional y sign. And the inside part is g x minus y e to the minus 2 pi I x minus y cosine dx dy. This part, this inside part, is actually, you can do a change of variable. It's actually a translation. It is g hat of cosine. And you don't have dx. And the rest thing is nothing but half hat of cosine. So you get it. Okay. So you can see that the key magic here is we switch the order of integration. And the reason why we are able to switch this order of integration is, well, your f, this function, capital F, first, it is smooth. Second, it decay. It decayed good enough. And of course, this in the future, in the real analysis, you may also learn this, and you can see, well, you may learn what kind of condition should be a good enough condition to guarantee you are able to switch this dx and dy. This is so-called the Fubini theorems. Okay, it's a very important theorem for in real analysis. Okay, so let me pause a little bit, and we will talk about the Fourier inversion. Well, in after 10 minutes. Okay, we'll resume at 19. So have a rest now, and let me try.
Okay.
Let's continue. Let's continue discussing about our Fourier transform. Okay, we now learn what is convolution for the non-periodic function. Now, what we are going to do is we will try to use it to find the inverse of Fourier transform. Now, let's say first we have a proposition. Before we do the inverse Fourier transform, we have the following proposition. Let's say fg are Schwarz function. Okay, then if you take this kind of sort of like the inner product as we did before, okay, you have f multiplied by g, but g is a Fourier transform of g, is equals to, you can change the hat. You can switch, you can try to give the hat to another function. Take the integral from -infinity to infinity and f hat g. Okay, so if you still remember, then this basically saying that, okay, if we change this g to be some h hat, then what we will get is h bar. Well, actually, you can either take this bar first or this this Fourier transform first. So it's bar here, let's say. It's f hat y h bar of y. Okay? Or if you try to define the inner product of two functions, non-periodic function, in this way. Then this means you can really switch this hat to either function. Okay? But they only have one hat. So this is a very interesting proposition. And then what we can do is we can somehow use this kind of hat proposition and use the fact that we know how to take the Fourier transform of the Gaussian, and the Gaussian is actually the good kernel. And then we can try to find this Fourier inverse Fourier transform, okay, of a function. We'll use this property, and the Gaussian is a good kernel, and the fact that we know what is the Fourier transform of Gaussian to find the inverse Fourier transform. Okay? So first, let's try to prove this. To prove this, again, we want to write everything super clear. So I will write it like this. Say fxy is equals to fx times gy e to the power minus 2 pi I xy. Okay, this is your new fxy. And then you will find that this fx g hat x, you can write it as fx g of c, right? Or g of y e to the power minus 2 pi I xy dy from minus infinity to infinity. The Fourier transform of g, you can write it this way, but here it should be c, but you want this variable to be called as x, so you want here to be x. Okay? So again, something similar happens, right? So if you take the integral from minus infinity to infinity fx g hat of x dx, what you should get is, again, a double integral of f of capital F x y dy dx. Okay? And moreover, f hat of y gy is again this one, but dx dy. And we use the fact that capital F x y is a good enough function. It decays as fast as you want, and it's smooth. So these two are equals to each other. Okay. Any question? If no more question, well, basically what we did here is just some algebra, okay? The difference here between the algebra is you have to name your variable very well clear. You must know what's a variable, what's a variable you are dealing with, and how you can name them smartly, okay? Now we are able to recover your function by the Fourier transform. Let's say f is a Schwarz function. Okay, then fx is the integral of f hat of c e to the 2 pi I x c dc. You can see that the only difference here is, well, I don't have, other than Fourier transform, I don't have a minus sign here. Okay. So this also means if you take the Fourier transform of this function, and then if you take another Fourier transform of it, what you will get is minus infinity to infinity f hat of c e to the 2 pi I x c with minus sign is, it should be, by this property, it should be f minus x. Okay. That clear? So let's try to prove it. So this also means if you take the Fourier transform and Fourier transform again, because you take it twice, you get from fx to f minus x. So if you take it 4 times, you get from fx to fx. Okay? So let's prove it. Let's prove it. Well, if we want to prove it, then the first thing we want to prove is a lemma. Or maybe this, I shouldn't call it a lemma. I will use it as a lemma here, but here it's actually a very famous theorem. It's so-called well, maybe I will mention the lemma later. Let's first do some trivial thing, okay? First, let's show that, well, you want to show fx equals to this, right? So if you plug in x equals to 0, what you want to show at the very beginning is f0 is actually equals to the total integral of your Fourier transform of function f. Okay, so why this is true? Well, this is true. It may not be easy to see, but let's try to do the following thing. Let's try to use the good kernel as we mentioned. Okay, let's call this G delta, which is the Fourier transform of our good kernel K delta minus pi delta x squared. Okay, then G delta hat of c is equals to K delta c. Okay, then if you take this integral of fx K delta x dx, what do we have? Well, this K delta x is actually G hat. Right? And by this property, we can change the hat. Right? So it's f hat times G delta. Okay. So what's this? It's the integral of f hat of, well, e to the minus pi delta x squared dx. But what is the left-hand side? Well, the left-hand side is nothing but f convolute with k delta evaluate at 0, right? Because k delta x is equals to k delta minus x. Then if you take this convolution, well, what you get is should be, well, kf, ft, and ft times, well, 0 minus t, k delta 0 minus t, and is equals to this, right? So now we can take delta tends to 0. On the right-hand side, you will have it tends to f, right? On the left-hand side, you can see that both of these functions are very good functions, so it will tends to 0, well, it will tends to f hat uniformly. So which means this, you can switch the limit and the integration. So what you'll get is f0 equals to f hat, well, this is x, we can also call it c, dx c. Okay? Is that clear? Any question? So now we have that 0, this is true. What if we don't have it at 0? If we don't have it at 0, the problem is still very simple because we can do a translation. Then what we have is fx is capital F0. And capital F0 is, by our property, is the integral from minus infinity to infinity f hat of c d c. Now, what is f hat now? Well, f hat now is you have a translation here of your function. Then on the Fourier side or on the Fourier transform, you should have a multiplication. This is a basic property of the Fourier transform. Okay? So you get it. Question? Any question? Any question? Okay, so we got the formula to recover our function by the Fourier transform, which looks pretty nice. Okay, so now the corollary is, well, Fourier transform is, it has the inverse, right? And well, any functions you can find the Fourier transform, and for any Fourier transform, you can get it back. And of course, you can see that, okay, if you take this, well, the inverse of Fourier transform is actually the Fourier transform cube. So this is actually a bijection on the Schwarz space. Moreover, it's actually more than a bijection. It also kind of conserve the one measure on this Schwarz space, okay, or one norm on this Schwarz space. So in some sense, you can think it's more or less like isometry on this Schwarz space. But of course, on Schwarz space, you cannot really say it has a norm like this L2, this kind of L2 norm. But in the future, you will see that we can actually extend this Fourier transform to not only the Schwarz space, but to a bigger functional space, okay, to a bigger function space. And in that case, you can see that this Fourier transform is actually isometry on this bigger space, okay? So this is so-called the Plancherel identity or Plancherel theorems. And it's actually an analog of the Passois identity. Okay, you can see why it is a parallel. It is a analog of the Passois identity. That is, if f is a Schwarz function, and then the norm, or as we define f and g, you can define the inner product of these two functions on the Schwarz space, fx g bar. Then the norm, as usual, is your f equals to g, and you take the square root. Okay? Then the norm of your function is equals to the norm of the Fourier transform of your function on this space, on the Schwarz space. Okay? And the proof is quite easy. You just need to make sure that you write everything carefully. Okay? Let's say this reflection of f to be fb. Okay, reflection and conjugate is f minus x with bar. Okay? And then what you'll find is, if you take the Fourier transform of it, since you take this bar here, so it's e to the power minus 2 pi I x c. If you take the bar, you will change this minus to plus. Okay, so it will equals to f hat of c, you take bar. Then what we can say is this, we can call this hx to be f convolute with fb at x. So it looks like the integral from minus infinity to infinity ft g, is fbt x minus t. So it's f bar x minus t becomes t minus x, right? dt. So h0 is the integral of ft squared dt. Is the norm of f squared. But we know that this is true, right? H of 0 is an integral of from minus infinity to infinity h hat of c d c, which is a convolution, so we can bring it back, and it's f hat times fb hat of c. And as we mentioned, fb hat is nothing but f hat bar. So it's f hat, you take the norm square. Okay, so we are done. So the trick here is how you can deal with or how you can write it super clear about this kind of, well, you change fx to be f minus x. You change this bar to be something like, well, minus x as well. So you must be very clear about the algebra. You cannot lose any minus sign. Okay, otherwise you may get something wrong. Question?
Sorry to interrupt, but I don't quite catch what is going on here from the FBX.
Here, right?
Yeah.
Here. So you see the FBX, if you take the Fourier transform, it's the integral from minus infinity to infinity, FBX e to the power minus 2 pi I x c dx, right? And what is FBX? It's actually from minus infinity to infinity, you have f bar minus x e to the power minus 2 pi I x c dx. And you want to make it somehow close to this, well, this f hat bar, right? So you want to make it longer. So it's minus infinity to infinity, f minus x e to the power 2 pi I x c dx, right? You change your minus sign to plus sign. Okay, so what's this? Well, if you have this kind of thing, then you probably want to say it's actually something like it is what? It is it is f it is f minus x. You take the Fourier transform, and then you take the bar, and then you evaluate at minus c. Okay. So if you have minus 1 here, you want to make a dilation, right? And this dilation is something, well, how could I write it as, maybe I will write here on the right hand side so that you will see it clearly. It's from minus infinity to infinity is fx e to the power minus 2 pi I x c dx. And if you take the bar, then that means you want this one, okay? And this is actually equals to this. By changing this minus x to x, then you have this minus sign here, and you have minus sign outside. You switch this minus infinity to infinity, so it doesn't change, right? So this equals to this. Well, I agree this is kind of messy about the sign, but I think for this part, you can see that these two are actually the same by doing a change of variable. But if you don't really do it by yourself, starting from very beginning and see whether, well, how you can get those kind of things, well, you may have no idea. So my suggestion is, if you try to make this minus and plus to be super clear, you may try to close the book and try to prove this kind of thing by yourself. Okay, try to do the algebra by yourself. I think that will make it a little bit easier to see why we want to define this FB. It's simply because when you take bar, then you have to have something like minus, so that it can somehow make this minus sign in front of your e to the power to be, well, doesn't change, to be something doesn't change. Okay, so this is actually equals to f hat bar. If you have minus sign, then you should get, well, you should get the plus sign without change.
I think it's still a bit confusing for me about why the FBX hat equals to blah blah blah. Because I am seeing. Oh no, it's something up.
Where? Up?
Yes, it's here.
This one? Okay.
Yes. I am thinking why it is not FB zeta or why it's not FB. Oh no, it's C, FB C.
Well, this is the definition of the Fourier transform, right? Or if you want to say we have this C here. Okay, is that a little bit better?
Oh, that makes sense.
Okay, sorry about that. Yeah, because yeah, this is something. Yeah, this is something. When you try to write something as a solution, this is something really confusing because sometimes you want to play with your functions and then try to do the Fourier transform and then take it as well as a new function with variable c. Okay, so sometimes this do think a little bit confusing. Sorry about that. Okay. Any other question? Okay, so this means, well, we can have this, well, the norm of a function is equals to the norm of the Fourier transform, which is why I'm saying it's kind of like the isometry, okay? Now, we have enough knowledge about the Fourier transform. Let's try to do the application to PDE, okay? Let's go back to PDE because eventually we want to use the Fourier transform on PDE and solve the PDE. Now you will see why we are so interested in this kind of Fourier transform because it makes the PDE much easier, okay? Okay, so first, let's see this problem, which is a heat equation on the real line. Okay, now you have a heat equation and well, it define on the real line and x is in R, t is greater than 0, and you have u x 0 equals to fx. You have an initial temperature of your solution, and you want to solve this initial value problem on the whole real line. Okay. Now the only problem or the only difference for us is from what we had before is, well, you can see that for the problem we had before, if we try to do the separation of variable, we may have some boundary condition on the stick, right? We have a stick and we may have some boundary condition on the stick, which we try to hit it. And then we ask, okay, what happens well, for this solution? And then what you can do is you can do the separation of variables, say u is equals to some function that only depends on t times some function only depends on x. Then you try to plug into this differential equation. What you find is, okay, then on time, it should satisfy this t prime equals to some t. So on time it should decay exponentially. But on space, since it is only finite length stick, right? So it should have utt equals to u, lambda times u, right? then in this situation, you will have, okay, u should be something like some cosine plus some sine, or is some kind of periodic function, because we're only interested in this bounded domain. So we can assume this function to be periodic function instead of something else. But now, if we are interested in a function that defined on the whole space, with initial value defined on the whole space, on the whole real line, then we may not be able to approximate this u in space by some periodic function. But instead, we can somehow use so-called, again, something like a good kernel, something like Poisson kernel, so-called the heat kernel. Which looks like this. Ht is k delta x, where delta equals to 4 pi t. Okay, so htx is equals to 1 over 4 pi t to the power half times e to the power minus x squared over 4t. This is so-called the heat kernel, and the Fourier transform of this heat kernel is equals to e to the power minus 4 pi squared t c squared. Okay? And we are going to use it. Why we are interested in this very ugly function? Simply because we have this function, right? We have this differential equation on the whole real line. Then let's assume ux0 is equals to fx. It's a Schwartz function. It's a super good function. Let's take the Fourier transform in x. Okay, so which means we multiply e to the power minus 2 pi I x c and take the integral in terms of x. What happens is, okay, the right hand side is still partial t u hat of c, right? And the right hand side will become minus 4 pi c squared, 4 pi squared c squared u hat c. Now, of course, it depends on t as well. Okay, so if we take the Fourier transform of this heat equation in x, what we get is ordinary differential equation. So we can get u hat of ct is equals to ac e to the power minus 4 pi squared c squared t. Okay? This is an ODE. I believe everybody knows this, how to solve this ODE, right? You divide this, u hat both sides, and then take the integral in t. And around the right hand side is minus 4 pi squared c squared t. On the right hand side is log u c, right? And here you might have plus some constant. So you should have this as your solution. That clear? So we have this, and what we also want is u hat at 0 should equals to the Fourier transform of c of f, right? The Fourier transform at initial time. So a c equals to f hat of c. So u hat ct should equals to f hat of c e to the power minus 4 pi squared c squared t. Great. If we know this, then how can we find u? U should equals to, you take the inverse Fourier transform of these two things, but you have the multiplication of these two functions. So it should becomes the convolution. Okay? And after you check the sign, it is actually the convolution of function of your initial data and the heat curve. Okay? This is a theorem. Let's say F is an SR is in the Schwarz space, then for any t greater than 0, we have, well, the function u is equals to f convolute with ht for any t greater than 0. Then the function, I'm sorry, I shouldn't write it this way because then it looks like you'll have Fourier transform. Okay, u x t is equals to f convolute with htx, and t is greater than 0. The function u is C2. It's actually C infinity. Okay, when x in R and t greater than 0. U solves the heat equation. It's actually very, very, very similar to what we had before about the wave equation. Okay, very, very, very similar. And second, uxt tends to fx. No, I mean not wave equation, but Laplace equation. Okay, uniformly in x as t goes to 0. Okay, so which means you somehow satisfy the boundary condition. And third, then we give it a name. If u is actually continuous, if we say u x 0 equals to fx, then we have u is continuous on the closure of the upper half plane. What is a closure of upper half plane? Is everything including the x-axis of upper half plane, okay? Or this set, x comma y, where x is in R and y is greater or equal than 0. Okay, this is so-called the closure of upper half plane. And thirdly, sometimes we write it as R squared plus with bar. Okay, this is a closure of upper half plane. And lastly, we also have the integral from minus infinity to infinity. It's not only converge pointwisely, uniformly, but it also converge this globally. As t goes to 0. Okay? I'm going to prove this. Before we prove it, any question? So this means, basically this means, if we define U as F convolute with so-called the heat kernel, then it is the solution that we want. It is a solution to our initial value problem. Any question before we move on?
Professor, one question. So when we plug on to the heat equation like ut equals to uxx, and we do the Fourier transform of both sides, and I mean, why does it preserve the taking the derivative of t, but it doesn't preserve when taking derivative of x. I'm not.
Well, you see, so this is first, this kind of calculation, again, is just a formal calculation, which is why we have to prove it. It is indeed a solution. Okay, this is first. And second, well, why you can just do it like this? Because, as we mentioned before, we take the Fourier transform in x, which means we multiply e to the power minus 2 pi I x c, and then take the integral. Okay? If you do it like this, then what happens is, since this partial t, since we assume that u is a very smooth function with very good decay, so we can change the integral and take partial t. Okay, so you can take the partial t outside of this integration. Then this will become the Fourier transform of u. This is first thing, you take the integration, that is a Fourier transform of u, and then take the derivative in t. But on this side, you will have this e to the power minus this kind of thing multiplied by this uxx, which means you take the Fourier transform of a function with second derivative. Okay, this is second derivative in x. So we know that the Fourier transform can change the derivative to multiplication. So which is why you will have the multiplication instead of the derivative. Okay? But the only reason why you have this partial t here, but you don't have partial x here, is you take the Fourier transform in x. Okay? If you take the Fourier transform in x, then this partial t is still partial t. But then partial x, it disappears. Because for partial x, you can somehow take the integration by parts. And then you will not have any derivative, but it becomes some times c squared. Right?
Yeah.
Mm-hmm. Any other question? So let's prove it. Let's prove that it's indeed a solution. First, well, u equals to f convolute with ht, right? So that means u hat is what? Well, u hat is f hat h hat. And this indeed becomes this thing. Right? So, okay, so we must have this u hat satisfy this ODE. So, since everything we have here decay fast enough, so we can switch the derivative and the integral, we can switch the order of integration any way we want. So we get this u solve this PDE. Okay, you can take the inverse Fourier transform both sides of this equation and get it back. That clear? So you can also say that since f and h are both smooth functions, smooth enough, so of course they are, well, they are C2. Okay, u is C2. So you don't need to worry about whether u is smooth enough or not. It's pretty good. And moreover, you can see that HT is well, it's a good kernel, right? It's a heat kernel, but it's also a good kernel. So the converge uniformly condition, this converge uniformly is for sure true, right? So it's actually the same as before. It's almost the same as we had before. We did before. Okay. The only thing that is different now is this uxt minus fx. This becomes, it tends to 0. Okay. So this one, this kind of thing is actually trivial in the periodic case. Okay. Because in periodic case, you only take the integration in a finite domain. You take from minus pi to pi, take this integral. So if you take it from minus pi to pi, what you will have is uniform convergence. Means, well, this two functions difference is super small, right? So uxt minus fx, it can be less than epsilon. So if you take this epsilon from minus pi to pi, it will still be very small. But now, what we are interested in this, well, is the infinite domain. Okay? For infinite domain, these two things are different. Converge in the integrable sense is different from the converge pointwisely. So this kind of converge, it tells you some global property. And then you can see that this global property is now different from this local property. Okay, which is why we still need to prove it. But the proof is also actually not so hard. We can write it. It's from minus infinity to infinity. F hat. You can take the Fourier transform. Well, because by the Plancherels, you can take the Fourier transform of it, which is square. And then here it becomes some application, right? E to the minus 4 pi square psi square t minus this is 1 square dc. Right? Now we can see, okay, this doesn't look so bad, right? We know that if c is super big, then this guy becomes super small because it decays a lot. But if c is not super big, then this power here, you can choose t. If c is not so big, you can choose t so that this power is super small. It's super close to 0, right? And that means this term is not so big. So let's choose t to be small so that t is less than, say, some constant times delta over n squared. This constant might be 100 or 1 million. Okay? Then what we have is the supremum of c is less or equal than n f hat of c times this guy. This guy is actually less or equal than 2, right? So times this e to the minus 4 pi square c square t minus 1, maybe with square, is less or equal than epsilon over 4n. You can choose n to be big enough, right? And you choose n to be big enough. This guy decay much faster than 1 over n squared. So you can choose it to be, well, epsilon over 4n. And then that means, well, for c is greater or equal than, for c is greater or equal than n, and your integration of f hat of c square is less or equal than epsilon over 2. Okay? If c is super big, then this integration is, well, is less than 1 over c squared. And is less than epsilon, right? If you choose n to be big enough. and c is less or equal than n of c square times e to the power minus 4 pi t c square t square, well, pi square minus, well, pi squared t c square. Now this guy, since you have t is very small, this is very close to 0, this minus this is something very, very small. Is less than epsilon over 4n. So the integral of c is less than n of c square. Let's say we have 8 here. Okay, f c square here, e to the power minus 4 pi squared t c square minus 1 is less or equal than epsilon over 2. Because the total length of your interval is 2n. Okay, so this integral from minus infinity to infinity f hat of c square times e to the power minus 4 pi squared t c square minus 1 is dc is less or equal than this number. Well, this number is when c is greater or equal than n, this number is less or equal than 2 squared, which is 4. So multiplied by this guy is epsilon over 2. And when c is less than n, this integral is less than epsilon over 2. So totally it's less or equal than epsilon. Okay? So you get, okay, so you get what you want. It will tend to 0 globally. Okay? Any question? And there is a direct corollary to this theorem, which is now if you look this u for any given t, you try to look this function in x variable. Okay, for any given t, it is a function in x. Then we can know that this function belongs to SR. And actually, it belongs to SR uniformly in T. In the sense that the supremum of any finite T x to the power k and partial L partial x L u x t. For any finite time interval, this guy is always less than infinity. Okay? K L t greater than 0. But this may not be true for t equals to capital T equals to infinity. Okay, but for any finite time interval, this u x t, well, is actually SR uniform in T. Okay, is that clear?
Sorry, could you like repeat this part again? I kind of
Sure. So you can see that for any fixed t, this uxt, for instance, t equals to 1. ux1 is a Schwarz function, right? ux2 is also a Schwarz function because it's just a convolution of 2 Schwarz functions for any fixed t, right? That's clear. But here, I claim that for any t, as long as your t is in some finite interval from 0 to capital T, for instance, from 0 to 100, then whatever t you choose, you get a Schwarz function. But moreover, this kind of Schwarz function, if you take this kind of things, try to estimate it, it is actually bounded above. Okay, it's always bounded above. Well, if we write it slightly in more details, that is, for any given t, for instance, t equals 100 or 200 or whatever, you have the supremum or the maximum of x to the power k partial x to the power l acting on u is less or equal than some constant that depends on L, depends on K, but also depends on T, right? T equals to 100, of course, you may get a different bound, and T equals to 200, it will also get a different bound, right? But here I claim is, well, actually, this kind of function is continuous in T. So which means this function is uniform continuous for any finite interval. You can imagine this is true. Okay, so which means the supremum t between 0 and t CLK t is less than infinity. It may goes to infinity as capital T goes to infinity. Okay, but in any finite interval, it is bounded above. Is that understandable?
Yes, I think I'm a little confused about the notation on the first line of the corollary. Like, what does it mean for U parenthesis dot? Is it a dot?
Oh, this one. This one just means that, well, you concentrate on this first variable, but try to treat the second variable as a parameter. Okay, so this is a very common notation. It just to say that now let's try to concentrate on the first variable, and the second variable is just something fixed. Okay, you can imagine when we use this notation, you can imagine t is a fixed number. For instance, t equals to 100, t equals to 200. Okay, and then in this case, we know that, okay, for instance, t equals to 100, u x comma 100 belongs to the Schwarz function. Belongs to the Schwarz space, okay? And u x comma 200 is also a Schwarz function, okay? And this means that t now is a parameter instead of a variable we consider.
Okay, thank you.
Any other question? Okay. Then now what we have is we have the existence of the initial value problems of this heat equation on the whole real line. Okay, we have the solution exist because we write it here, right? We write it down. Now we still want to ask ourselves, remember, how about the uniqueness? We don't really care about whether it's well posed or not, but the existence and uniqueness are always very important. Okay? By the way, I'm not going to prove this. You can check it from your textbook, and you can also try to understand it this way. The proof is, well, is quite standard. Okay, you can check it yourself. So now we know the existence of this initial value problem, but now we want to say, okay, how about the uniqueness? Here is the theorems about the uniqueness of the problem, which is a very interesting thing to state, and the proof is very, very interesting. Okay, now suppose you have a solution. UXT satisfy first, U is continuous on this closure of upper half plane. Okay, and second, you satisfy the heat equation for T greater than 0. And thirdly, Ux0 equals to 0. Okay, And fourthly, we still want it to be Schwarz, okay? This kind of function is in Schwarz space, uniform in T, as we said before, okay? The conclusion is U must equals to 0. Okay, so which means if you have two functions, if you have the two solutions, you take the subtraction of these two solutions, then it will be a new function that satisfies the heat equation but with the initial value 0. And we claim that then this function must equals to 0, which means you cannot have two different functions both satisfy this initial value problem. Okay, any question? The proof is quite elegant, I have to say. The uniqueness proof is always something like this, which is if you try to say something is unique, that means you cannot build anything starting from 0, right? How you can say this kind of statement is true? Well, the key idea is you try to build some energy function, and then you prove that this energy function, actually, if it satisfies your differential equation, it should dissipate, which means the energy should decay. Like if you have the heat equation, then the heat will somehow try to distribute to the infinity. It will try to go to the infinity. So which means it's somehow diffused. The energy will diffuse. Okay? So this is what we try to do. We try to define the energy function to be, well, from minus infinity to infinity, uxt squared dx. Okay? If U is a temperature, then this basically like the kinetic energy. Oh, I mean the internal energy. Okay? So then we can see that if we know that E0 equals to 0. If we can show E constantly equals to 0, that will imply U constantly equals to 0. Right? So this is what we want to show. But here the idea is we will show that because this is an energy function and each time you will have a fixed energy. But then if we try to take derivative, we will show that the derivative is actually decreasing or at least not increasing. Then we know that, okay, if it's starting from 0, it will never go to something positive. It will always keep 0. Okay? So why is that? This is something you have done before, okay, in your homework. Let's take derivative. So if you take derivative, it will be this plus u partial t u bar. And we know that partial t of u equals to uxx. Right? Now, what we can do is we can do the integration by parts. Although it's from minus infinity to infinity, but we can do the integration by part because at infinity, your u equals to 0. So on the boundary, if you write it as a limit, then this boundary term from minus n to n evaluated, it will tend to 0 because your u in x is a Schwarz space. It's in Schwarz space. So it's equals to from minus infinity to infinity with a minus sign, will ux u bar x plus ux u bar x, which equals to minus 2 from minus infinity to infinity ux squared dx less or equal than 0. Okay, so this means et decreasing in time, then well et equals to 0 for n time. Well, maybe you will ask, we just do this kind of formal calculation, right? It seems that we use nothing about this kind of continuity condition or uniformly Schwarz space, this kind of condition. Then why we need this kind of condition in terms of getting this guarantee, this uniqueness of your solution? Why do we need this? This is something I would like to ask you to check. I will not assign it as a homework because it's kind of tedious, but you can check that this kind of integration by parts, or you try to plug in ut equals to uxx, this kind of process, some steps you do need those kind of Schwarz condition or continuous condition. Okay, but I will ask you to check it. I will not check it for you. Okay, the formula you can see that you can prove the uniqueness by checking this energy function of U. So that's all I would like to discuss today. And on Thursday, we will discuss more about PDE. And we will try to move from Stan's book to Strass' book, okay? And talks more about some, more concretive tricks about PDE, about how you can solve a PDE like an engineer, okay? Maybe not like a mathematician. I will still